Okay, so we'll go over some multi-threaded coding examples. To do multi-threaded programming in C++, we have to include a header file called pthread.h. The P stands for POSIX. I don't know if POSIX has come up. That was a consortium of, I think, POSIX is Portable Open Systems for Unix or something like that. So a group of people got together so all the Unix systems could all communicate with each other and came up with a way for doing threading. So this actually got added to the C++ language after the language came out. So now what we're going to do is we're going to have a function. Now when we go to create a thread, we're going to call a routine called pthread_create. This method comes from that header file. The parameters to that method are going to be, the code that we put on a separate thread is going to be a separate function. So we now have to pass in a parameter to pthread_create that says here's the function. So we have to actually give a kind of like a function name as a parameter to another function. And this is where the concept of a function pointer came up. I know we talked about, we had some homework question a while back about function pointers. But this is where they come into play, is that we're going to need to pass a function as a parameter to another function. So this ends up being the address of pthread1. So that's going to be, I'm sorry, pthread1 in this case, this is the actual thread itself. This is attributes about the thread, and only in special cases are they non-null. So in all examples, they'll all be null. This is going to be, this is going to be the name of the function that, where the code that runs on this thread will be. And then we also have the ability to pass in parameters to the function. And this might seem a little bit strange, but we're going to take the parameters and cast it to a void pointer, meaning a pointer pointing at nothing. It sounds strange, but the reason is we could pass in characters, we could pass in integers, but we're actually passing in a pointer to something. So whatever the function does, it will cast it back to whatever it needs to be. So it's a little getting used to, but we're casting this to a pointer to void.
Is the first parameter always thread 1, thread 2, thread 3, like that's...
It would end up being, yeah, it ends up being the thread itself. So we create, I'm sorry, so right here we have there's a type called pthread__t. This is actually, these are two objects, thread 1 and thread 2, are of type thread.
Got it.
So we can create as many of them as we want, however many threads we need, you just create these two threads. I'm now going to give them a message as a parameter. So I'm kind of just, I don't have to do this, but I'm just passing in a parameter to the thread. And then at this point, after the create is done, these two threads, which are actually in this case is pretty simple, I'm calling the same exact function. So I'll have one function, two different threads are going to run the same function. And when we call this, as soon as the create is completed, this function will now be running on a separate thread. So we'll start to create the second one, and at that point, technically, the first one could be time sharing with the main function. So there's really, in the end, there's really going to be three threads: the main function that created the two children threads, and then all three of those are technically sharing the processor.
So this function pthread_create.
Right, this function.
Returns an integer.
Right, and that's going to be.
Because it's like 1, 2, 1, 2, 1, 2, 1, 2, like that?
Well, no. It's going to return an integer, which is going to be its return code. Like, did it successfully create a thread? Did it fail?
0.
And we could check it. No, there's like a different set of codes. You got to, I guess, look up on Google. But did it work successfully? Did it fail? Why did it fail? And that kind of thing. So, yeah. So the signature for the pthread_create is a thread variable, attributes about the thread, a pointer to the function where the code is going to be, and then parameters to that function, if optional parameters if you want to pass parameters in. So at this point, the two threads have been created, and now they're running independent of the main thread. These two lines that say join are basically saying the main thread doesn't want, the main thread now can really keep going, independent of the two children thread. But we're saying we want to wait here until thread 1 finishes. And then once thread 1 finishes, I don't want to make any progress until thread 2 finishes, and then I'll make progress. So the main thread can stall itself out waiting for the children threads to finish. That's optional. So that's just what we're doing here. And then this will say thread 1 is done, thread 2 is done. So now the body of the threads is the function. Right, there's not a whole lot. The body is, what are we doing? We're saying as I goes from 0 to 19, we're going to, so now we're getting the pointer, which is the string thread A or thread B is coming in as a parameter. And all this thing is doing is printing out thread A or thread B, and then, yeah, it's going to print out thread A or thread B, and then the which run from 0 through 19. So what would you expect the output to look like for this?
Thread A 19 times, thread B 19 times.
Okay. But let's see. Would it be like exactly in that order? Or, so wait, you would expect to see, assuming it ran sequentially, you would expect to see thread A 0, thread A 1, thread A 2, thread A 3, up to 19.
Right.
Then thread B 0, 1 to 19.
Right.
If they ran sequentially.
Well, because the way you said that thread 1 will wait, or thread 2 will wait until thread 1 is done, I don't know.
No, I'm sorry. The main, so there's really 3 threads. The main one is also kind of considered a third thread, right? The main one spawned 2 children threads. So thread A and thread B were started by the main one. The main thread will end up being stalled, so really only thread A and thread B are going to run until they're both finished, and then the main thread will continue. So we'll have thread A and thread B both running, but they'll be running together with each other, not sequentially.
Because I would think that the goal would be to say thread A1, thread B1, thread A2.
Where it does a
like
perfect
that,
back and
where it kind of
forth.
goes back and forth.
Okay.
But
Well, I think the next example does something like that. But right now it's kind of a free-for-all, right?
okay.
So thread A could start running and print out 0, 1, 2, 3. Then maybe thread B takes over, and that goes thread B 0,
There's
1,
no
2, 3, 4.
order at all.
There's no order, right? We don't determine when we can start and stop. We're just, the 2 programs are running separately of each other. So let's compile it and run it. And also one thing you have to do when you compile is you have to say G++, that's the GNU compiler. Now you have to add an option -LP thread. And then, what's the name of it? Simple thread. Simplethread.cpp. So I got a warning that something is depreciated, something's going away from the compiler, but that's okay, it's just a warning. So now if I say run it, stretch this out. Stretch it long enough. I was hoping to get it right from the beginning, but it's a pretty close one. Okay, so this is the whole output. So it looks like the 2 different programs, which were kind of doing the same thing. They were just saying thread A was trying to say thread A 0 through 19. Thread B was trying to print out thread B 0 through 19. But they're randomly stopping and starting, and it's not controlled by us.
They like collided in the middle.
Yeah, so it looks like what happened was, it says thread A0. Now, after every time we do what's behind here, I say thread A0 and I go new line. The new line didn't happen yet. And then thread B started running. Then thread B was trying to say thread B0, but it never printed the 0. Because then thread A took over, and then thread A had a pretty long run. It went down
Until
to
the 0 came
it
in.
went down to 11. This 0 is the 0 from thread B from a while ago. So thread B picks up where it left off. Then it looks like thread A started up right away again. And it printed out thread A, and then immediately it was gone, and then thread B printed out a 1.
And then immediately the 12.
The
thread
12
A.
from A from before, right? So it's like, we don't control when they're starting and stopping, it's kind of random. And actually, if I run it again, the results are gonna be different. This one went a little bit better, right?
Yeah, that one went how I thought.
Wow, that one went almost perfect, right? A ran through 19, then B ran,
Through 19.
then A finished, and then B finished. Wow, that was, hold on, let me try running it again. All right, this one ran a little bit better, but there was still some cutting and dicing, right? So this one, A went through 3, then B, this looks weird. A seems to have a lot more dominance over B.
Yeah.
But, because then B ran, but then immediately A ran and did 4 through 19. Then B picked up, that's the 0 from before, and then B was the only one running at that point. So, yeah, it's just, basically it's two different programs running kind of independent of each other. Get a good, I keep running the same output, hoping for,
That one's a little more dicey.
yeah, I guess B got a kind of a good run in the middle at this point.
Yeah, B.
So this 0, that 0 is from B, that 8 is from A, and then the blank line, that must be A doing a carriage return and then B taking over and finishing its carriage return. That must be where the blank line's coming from. So,
And then A takes over when it's on the line, same line as the B.
yeah, so before it could even do its carriage return, A started running.
Because the return is up there now.
Wait, which, for this one?
Because
Well-
that one space is up there, right? The space that comes before thread A10
Oh, right, right.
is up there.
Yeah, it's up there, so that's why it didn't start on a new line. So yeah, so basically, I mean, you kind of get the idea. It's two different programs running, and they're both doing the same thing. They're just printing one to 0 through 19. But we don't control which one starts and stops. So it's really just two different, our one program is splitting off, I guess, two different children programs that are, we now don't have control over how much time the operating system gives to one and the other. Just one runs for a little while, then the other runs for a little while. So at first it seems, why do this? Why not have it sequentially? But for our example, like for our clock radio, we want one thread to run the clock and another one to say, what would you like to change the time to? So, let's see, anything else interesting about this example? Okay, so let's look at a different example. This is one now where we're going to introduce locks. Okay. So, the example starts off using something new now. I'm introducing a lock. So now with two different threads running at once, we start to realize one could be in the middle of updating some variable, or a set of variables, and then the other one starts running, because we can't control when one thread stops and the other one starts. The other one can start running, and then it starts updating those same variables, then the first one comes back and finishes up its update, and now the whole set of variables is all screwed up. Neither thread wanted them in that state. So it might be a good idea if we're going to update something, any resource like a file or, pretty much anything the two threads share, if we're gonna make updates to it, we wanna be able to have a mechanism where once we start making our updates, no other thread should then start its updates until we declare ourselves finished. So the way we'll do that is we'll create a variable which is called a mutex, a mutually exclusive variable, meaning only one thread can own it at a time. If I own it, you can't own it. If you own it, I can't own it. So we can get access to the variable, and then at a later time we can give up access to it. But that will stop any other thread trying to touch the same resource. So we create, in this example, we're going to have 3 separate functions, and we're going to also use 3 separate locks, mutex variables, we'll call it. So in this case, we're going to have a producer function, a consumer 1, and a consumer 2. And we're going to start off by having out of lock A, B, and C, we're going to start off having lock B and C are closed. So if anybody wants to use lock B and C, at the moment they're going to have to wait. The only lock that's open is lock A. So then, just like before, I have a message, thread 1, thread 2, thread 3. I then go and create 3 separate threads, 3 different children threads. The main routine is going to wait for the 3 to collect together, to complete before it goes on. So now we'll take a look at what these threads do. And we'll edit these, and we'll play around with them just to see the different effects that the locks have. So the thread that I'm calling producer, these names don't really mean too much, but basically, right now the way this is set up, the 3 threads are sharing a variable called thread run. So I'll let like 20 different runs of a thread run, and then the whole thing will stop. So what is this first thread doing? The first thread is getting access to lock A. So what does that mean? If it gets access to lock A, then any other thread requesting lock A cannot proceed until this thread gives up lock A. Okay, so now what this thing is doing is it's saying, I get lock A. Now what if this thread started running? We said we initially locked out lock B to start with, right? So this one's going to get stuck right here. It's not going to be able to proceed, because what the function lock does is says if this lock is available, I will grant it to this thread and I will let the thread keep going. But if this is not available, I'm going to make it stop right here and say that's it, time's up, let someone else run.
Available just means that there are no locks.
Well, okay, that's a good question. Available, the lock is either, not sure if lock is the best word for it, but if it's a resource you're trying to grab, and if you can grab it, like you're saying, I want to proceed, but before I proceed, I want to make sure I have like permission to proceed. So if lock B is available, you're saying I would like to touch the resource associated with lock B. Like let's say it's a variable. You want to write to it. So if it's currently not locked out, then what you do is they give the lock to you, and now you can proceed and edit it. But if somebody else then right after you tried to get that lock, they would get stuck. It would be like they're being told you have it, so they have to wait.
Is it kind of like a key? It's like you're not giving the lock, you're giving the key or something. Because then you're allowed in.
You can kind of think it like that. Yeah, you're allowed in. So you're like, there's one key, and they give you. You can say it's like kind of like you're saying, "Can I have the key?" If you get the key, you can go in and you lock the door behind you.
Right.
Then you can do whatever you want until you come out and give the key back. So the operating system's kind of managing a key, I guess. Yeah, that's why maybe lock's not the best way. It's like because you're getting permission to it. So at the beginning of this code, I said lock A is the key is available, but for B and C it's currently not available.
Mm-hmm.
So the 3 threads, producer, consumer 1, and consumer 2, all 3 start at the same time. What would happen if thread, let's say this thread ran first, and it tried to get lock B. Lock B is not available. Nobody had, right, because I started it off saying it's unavailable. So this thread would actually get stuck. Let's say this one ran next. It asked for lock C, it will get stuck. What's the only one that can proceed? A, because that's the only lock I started off unlocked, or the only key that was available at the time. So the output should then, of these three programs running simultaneously, the only one that can proceed and print out is this one, producer in critical section. So the critical section is generally considered in operating systems terms the part of the code that the thread is writing to the same variables or sharing the same resource, that you want to make sure only one is running at a time. So that's what, that section of code is called the critical section. So all I'm doing here is just printing out I'm in the critical section. So even though these three threads will run independent of each other, I can be guaranteed this is the first line of output, because this line and this line can't get started because this is locked. Now, after the output comes out and says producer in critical section, what's the next thing that happens? Remember, this thread and this thread are still stuck. They're not going anywhere. Now I say unlock, which is actually a method that comes from that pthread header file. Pthread mutex unlock is a routine that basically says I'm returning the key for B. Now, this might seem a little strange because it locked A and then returned the key for B.
So when you unlock something, you're automatically locking up what you previously had unlocked. Like A is unlocked.
No, see.
A has the key.
No, right now, it's like there's three different keys. There's three different, what they call locks. So I'll say locks, you can think of them as keys. But this routine grabbed and is currently holding lock A. You could kind of think of it that way, but now that we're actually causing these routines to signal each other, it's actually like they're passing the key to the next person. So anyway, this thread got access to lock A, so it's currently holding lock A, and then it actually is giving up lock B. It seems strange, it's like it's giving up a key it doesn't own, but it's basically saying the key for B is now available, or the lock for key for B is now available. So that means now if there was any routine that was waiting for B,
It can run.
it can now run. It will now grab the resource B and it can run. And if somebody else now tried to ask for B, it would get stuck. So the whole point is, like, once you lock something, nobody else who's also trying to lock it will be able to get that resource. The code inside this method, the code looks something like this. It would say, if, let's say B was a variable that was equal to 0 or 1, 1 meaning the thing is available, 0 means someone else beat you to it. The code would say, if the variable equals 1, then make it equal to 0 and proceed. That would be that would be the whole function. If the variable equals 0, means somebody beat you to it, then there's some code that makes your thread get moved somewhere that causes it to stall. And only when someone does an unlock do you get moved back into an uninstalled state. So it's something like that. It's kind of an operating systems thing, but that's really what that code is doing. So in this case, what is happening? The first line of output of these three threads should be producer in critical section. Then it unlocks B. What does unlock B do? Well, this guy was stuck before, so this guy can now proceed. And then you'll see consumer 1 in critical section. What does it then do? So this guy's still stuck because this guy, after he unlocked B, could have looped around again and got stuck waiting for something that he actually locked himself out on. So this thread is counting on somebody unlocking A so it can continue. So now C gets unlocked. What does that do? That causes this thing to now start moving again. And this will print out consumer 2 in critical section. then this one unlocks A, which gets the first one to run again. So this is kind of what you were saying before, like coordinating this one. You'd like this one to go first and this one second and so on. So the output of this program should be producer in critical section, consumer 1 in critical section, consumer 2 in critical section, producer in critical section, consumer 1, consumer 2. They should keep, they're now signaling each other like I go first, you go second, you go third, then I go, you know, something along those lines. So if we run that, that should be the output for this. And then we could just playing around with the locks. Just playing around with the locks, we should be able to make them go in different orders. So let's see, if we, what do we call this thing? This was called zeros, producer, consumer. Yeah, I must have put in spaces for consumer 1 and 2. Okay, gotta put these spaces in here, here and here. But basically the output is producer in critical section, consumer 1, consumer 2, producer, consumer 1, consumer 2. And now we're like making the 3 threads run in a particular order. Suppose we wanted to have, so generally this is kind of known as the producer-consumer problem. So if you look that up on Google, you see tons of write-ups on it. But generally there's one producer and one consumer. So it's like the producer gives a page of data and then the consumer prints it, and then the second page comes and the consumer prints it. So that way you're not printing, it's not like 4 pages were handed and then the printer printed the 4th page, not the first page, like they're signaling back and forth. But we can make these things signal to each other in any way we want. So let's say, for example, we wanted to have the producer produce something and let consumer 1 handle it. Then the producer produces a second thing and lets consumer 2 handle it, like fans them out, 1, then 2, then 1, then 2. So suppose we wanted the output to say, producer in critical section, consumer 1 in critical section, producer in critical section, consumer 2. So it goes producer 1, producer 2, producer 1, producer 2, over and over and over. How could we play around with the locks to do that? We could start off with A being the only one unlocked, so that will guarantee that the producer will run. Then we would unlock B, so we want consumer 1 to be waiting for somebody to unlock B. When it's done,
It goes back to A.
okay, yeah, let's try that. It goes back to A, and then when goes back to A.
Oh, but then it's just gonna go B again. When is C gonna get a chance?
Yeah, this, if we did it this way, C would never run, right?
Right.
So let's just, it's good to go over these examples. Yeah, this is doing producer 1, producer 1, producer 1, right? Producer 2 got locked out. Okay, pretty much we're good. Now suppose we wanted to, how can we make them go back and forth? We could make consumer 1 waits for B and releases A, and consumer 2 waits for C and releases A. We could cut and paste, we could do this. Copy. This waits for A and then releases, locks A and then unlocks C. Will that work? Let's see. So the producer, the producer's the first one to start. It produces something, then it wakes up B.
That one doesn't unlock anybody.
Oh, what am I doing here? I gotta change this to A. Then this one will unlock A, which will allow this to continue, and then this will...
Will it continue? Or will it go back to the top?
Well, no, so this is going to look for lock A, which will initially be available, it will produce something, then it will, this signals this one to proceed.
Mm-hmm.
When this one finishes, this one will now get stuck because it needs, it already got the lock for A. It needs something has to unlock it for it to proceed. So it's not gonna be able to get, it's gonna get stuck here. Waiting, I gotta change that to an A, hold on. And then, so that will cause this unlock of A, done by consumer one, will now cause this to continue. And then this will do an unlock to this one. This guy will continue and bring us back to this
A.
one. Yeah. So this should now, the way we played with the locks, it should go producer, consumer one, producer, consumer two, and do that over and over. Let's see. Okay, so yeah, that did work, right? But for some reason it didn't finish. Let's figure out why it didn't finish. But anyway, the producer thing ran, consumer one picked up the work, handled it. Producer ran, consumer two. Producer one, producer two, one, two. So we can actually, now we have 3 different threads, and just playing around with the locks, we decide what order they can run in. It actually didn't finish, so let's see. 1, 2, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16.
Supposed to do what, 20?
It was supposed to do, I said max runs to 10. Let's start with 0, and each time we do a run, we increment the run count and then make sure it's less than 10. So it should have done 9 runs. And it's somehow it got stopped in the middle. Let's try to figure this out. Oh, wait a minute. A producer run actually does 2 things per run. So this and this were considered 1 run, right? So it's 1, 2, 3, 4, 5, 6, 7, 8, 9,
10.
10, 11, 12. Is that right?
But it didn't finish.
Right, it seems to have gotten stuck at the end of the second consumer. The producer didn't run again because it unlocked A and it came around and bumped up the count to be out of bounds. And then when A went around to the top, it was too high.
It didn't go.
So A was done, A's done, this guy was probably done, but this guy is still stuck. Because this guy doesn't wake up until the producer produces and then wakes him up. So this thread finished, but this one is still not finished. It's still in its loop. It was stuck. That's why it didn't come back.
But then why didn't producer print out again?
So what happened was, after this guy finished and unlocked A. And let's say producer was, let's say the producer thread unlocked C and then timed out. Then this thing continued, printed out consumer 2 in critical section. Then it locked A, which would make this thing, if it ever started running, continue. This guy went up and bumped the count. Oh, I'm not bumping the count here. I should be bumping the count here. Okay, but that's why it went above 10. Okay. But anyway, the reason why the program didn't end is because at least one of the threads is still in the middle of running. And the reason why it was running was, This one came around, and now let's say thread run was high enough that this loop stopped running. This would terminate and this thread would finish. The loop up here would go around to the top, it would terminate and finish, but this loop was still stuck on this lock right here and never finished. So let me add in that plus plus. And I'm still thinking it might hit the same problem. But it's just something good to, what is this?
Is it open at the bottom?
No. Okay. Yeah, that one finished correctly. One, two, three. There should be a total of 10 runs or 9? No, I guess 9. Because we started at 0, so it's 1, 2, 3, 4, 5, 6, 7, 8, 9. But if I made it go to one more, the lock would happen, and then one thread would be signaling another one to run, but the other one, the thread count would have been so high it's done. And that'll end up getting stuck. Yeah, let me add one more.
Consumer 1?
Yeah, so if we add one more run, so I make it go 11. What should happen now is it should not finish. Yeah, okay. So this is just pointing out another danger to using this. What happened here was there's a total of 11 thread runs. Right? We have one variable counting how many times a thread can run. The first thread, the producer one, ran once, then the consumer 1, consumer 2. So this is 3 runs, this is 3 runs, this is 3 runs, and there's still one more run left. And what happened on the last run was it signaled back to the producer to run.
But the thread count was as...
So it should have, actually, it should have said producer in critical section, right?
But the...
Oh, no, wait, hold on. After the third, the consumer 2 finished, that was the 10th, that was the 9th run. When this one finished, the count was 10. After this one finished, the count was 10. This thread is in the stuck state. It's waiting to be woken up again. So then, after it hit 10, we went up to here. This thing saw the count was too high and finished. This one is still stuck. It's not finished. And then this one could have looped around and saw that the count was too high and it finished. So thread A and thread C would be finished, but thread B would still be waiting for thread A to, say, wake up and start consuming the thing I produced. And that's why it's not finishing. Okay, the last example, just go over this one quickly. It's a good example, but this is an example of what they call a condition variable, and this is when what will happen here. Suppose it turns out that, so the top part is pretty much the same as the previous example. Suppose the variable that we want to read and update let's say in this example, this was kind of almost too simple of an example, but I'm sharing a variable called count. They both of the two threads share this variable called count. And what I'm saying is each thread has a simple job. It increments count. Right? So each thread can run and say, I'm going to increment count. Okay, now I'm going to increment count. And the idea is that one of the threads, the first thread, if the variable count is between two numbers, count 1 and count 2, it should not run, it should wait. And the other thread should be able to increment it anytime it wants. So the first thread can increment the variable anytime it wants, but the second thread can only do it sometimes. So here's the thing, we have to lock out something so we can operate on count. We want to see if count is between a certain number of two or not, then we're allowed to increment it. We'd be allowed to increment it. And if it's not between if it's somewhere between, I think I set these up so it's like between 3 and 6. Yeah, so basically the two threads are going to take count, which starts off at 0, and they're both going to run independent of each other, and as each one runs, it will take count and add 1 to it, until it finally hits 10 and then it'll stop. But we have a special stipulation that one of the two threads is not allowed to operate on the variable. If the variable count is between 3 and 6, one thread should get stuck and the other one should be proceeding. So the output of this should be like each thread gets to update it, but between 3 and 6, only one thread could do the work. So let me bring up a window and just compile it. And so it's G++ dash be threaded, and this one's called condition variable. Okay. And then the output will be okay, so what's happening is once the value goes above 3 and less than 6, only thread 2 can do the incrementing. From here and here, either thread could be doing it. But in the middle, it has to be thread 2. So, you know, you could change that into whatever condition you want that makes sense in the real world. But only thread 2 can do the incrementing. Only thread 2 is allowed to do the incrementing when the value is between 3 and 6. So thread 1 says, while count is greater than 3, greater than or equal to 3 and less than or equal to 6, I want to force myself to stall. And then the only other thread that will be operating is thread 2. Thread 2 says as long as the count is less than 3 or greater than 6, I want to wake this thread back up. So this one will put itself to sleep and this one will wake this one up when the condition that makes it sensible to wake it up happens. And that's what this signal and wait routines are. So wait is going to act a lot like the lock routine we just did before. Now here's the only issue. If we get a lock on the variable count to see what its value is, and then decide we want to put ourselves to sleep, we need to give up the lock for count so the other thread can use it. And so what we'd end up having to do is we want to simultaneously put ourselves to sleep while freeing up a lock. So this is a scenario that comes up. It's called a condition variable. It's a scenario that comes up when we want to, the variable we're looking at, count, we have to lock it out before we can look at it because we're also incrementing, we're changing it. If we lock it out and read its value and go, oh, based on that value, based on this condition I'm in, I should put myself to sleep and let the other thread do all the work and then allow the other thread to wake me up at some point in the future. Well, I now have the lock. I have to give up the lock. before I put myself to sleep. So one thing you could do is you could say, step 1, give up the lock, step 2, put yourself to sleep. But now you get into a situation where right after you give up the lock, suppose you then time out and the other thread starts running, and the condition that made you think you should go to sleep has now gone away, so you should stay awake. So then you think, well, I don't want to give up the first lock before I put myself to sleep, so maybe what I'll do is I'll put myself to sleep first and give up the lock second. But once you put yourself to sleep, you'll never give up the lock. So there has to be a step where you put yourself to sleep and give up the lock all in one step, and that's what this condition wait routine is. So what I'm basically saying here is, this lock that I acquired up here, I'm giving it up, but then I'm locking myself on this thing. And now I'm waiting for somebody to signal me to wake me up. And that's going to be done down here. That's going to be done here. This signal condition, COND variable, is going to make this thread wake up and start running again. And that's how we got the output that we got. So what happened here was, when the 2 threads started, each of the 2 threads are running, and they're each trying to increment count. But once it got to the point where the value of count was greater than or between 3 and 6, equal to 3 or, well, thread 1 happened to raise it up to 3. So once it got to equal to 3 or greater, from here to here, we are guaranteed that only thread 2 was alive and running. Once the value got incremented to 6, then thread 1 was signaled to now wake up, and it became a free-for-all again. 1 or 2 could be doing it. So if I run this if I run this output over and over, I would be guaranteed that the thread that made it go from 3 to 4, so the thread that outputted a 4, 5, and 6, once it hits 6, then thread 2 wakes up thread 1. So only thread 2 could make it a 6. So 4, 5, and 6 will always be done by thread 2, and all the other ones could be 1 or 2. So actually, if I ran this output several times, I can just be guaranteed that the 4, 5, and 6 would be thread 2. See, this result is a little bit different, right? No, same result? Same exact result, right? Maybe I should put a stall in here. They're coming out almost exactly the same every time. It looks like it's moving so fast, I guess, that the first one that kicks off is incrementing it up to 3, but the way the code was written, any one of the threads could have done this. And then 4, 5, and 6 would have to be done by thread 2, and then 7 through the rest of them could have been done by either thread. It's not locked 3 through 10, right? 3 through 6, where it's locked. Okay. So yeah, as long as it's between here and here, it won't wake it up. So is the first thread put itself to sleep once the value hit 3. And then the second thread woke up the first thread once the value was beyond 6. And then they were both alive again.